One burned fuel so corrosive it destroyed its own engine from the inside out, and they ran it for years anyway. Another stretched across 2 full city blocks and required a crew member whose only job was to watch the middle of the machine. A third carried its own power plant from a naval warship, bolted it into a locomotive body, and set a national speed record on a Tuesday afternoon. These were not prototype disasters. These were deliberate, singular acts of engineering ambition. Here are 10 bizarre locomotives, so strange they only built one. Number 10. The Chesapeake and Ohio M1 Steam Turbine Electric. Every steam locomotive ever built connected its boiler directly to its pistons directly to its rods, and its rods directly to its driving wheels. One continuous mechanical chain. Unbroken. Universal. The C&O M1 broke that chain entirely. It used a coal-fired boiler to generate steam, fed that steam into a turbine, used the turbine to spin an electrical generator, and drove its wheels with electric traction motors. The same way a diesel-electric did. No pistons, no main rods, no crossheads. Baldwin Locomotive Works and Westinghouse Electric built 3 units, numbered 500 through 502, delivered in 1947 and 1948. Each measured over 154 feet from nose to tender end, longer than a regulation football field from goal line to goal line. The locomotive unit alone weighed 856,000 pounds, with a boiler pressure of 310 pounds per square inch and a rated output of 6,000 horsepower. Within months of entering service on C&O passenger runs between Washington and Cincinnati, railway workers had named them sacred cows. They cost a fortune, consumed extraordinary amounts of coal and water, and the turbine electric drive proved chronically unreliable. All 3 were withdrawn by 1950. Everyone was scrapped. The C&O built 3 of the most technically ambitious steam locomotives in history, ran them for less than 3 years, and the world had seen enough. Number 9. The Pennsylvania Railroad S2 steam turbine. The rule said steam meant pistons. Steam pushed a piston. The piston drove a rod. The rod turned a wheel. Every mainline steam locomotive ever built followed this sequence without exception. The S2 had no pistons, no cylinders, no crossheads, no main rods. A direct drive steam turbine, geared to the driving wheels, replaced the entire reciprocating system. The result required a wheel arrangement, 686, that had never existed before and has never existed since. Baldwin Locomotive Works delivered 1 unit in 1944. Wartime restrictions on lightweight metals had forced heavier construction than originally intended, requiring 6-wheel leading and trailing trucks simply to support the added mass. The forward turbine was rated at approximately 6,900 horsepower. Driving wheels measured 68 inches in diameter. Testing on Pennsylvania Railroad main lines confirmed smooth, vibration-free running at high speed, exactly what the design promised. But fuel and water consumption was enormous, and the turbine proved sensitive to the grit present on any working mainline. The S2 was retired in 1949 and scrapped. No preservation effort was mounted. The 686 wheel arrangement died with the only locomotive that ever carried it. Number 8. The Norfolk and Western TE1, John Henry. By 1954, the rule was settled. Diesel had won. Every major American railroad was converting, and the engineers who still believed in steam were running out of arguments. The Norfolk and Western built one final argument and named it after the folk hero who raced a machine and won. The John Henry was a steam turbine electric locomotive. A water tube boiler operating at 600 pounds per square inch fed steam to a turbine connected to a generator powering electric traction motors. Baldwin Lima Hamilton and Babcock and Wilcox built 1 unit, designated TE1, delivered in 1954. It weighed 818,000 pounds and was rated at 4,500 horsepower. The N&W tested it in coal drag service on their mountainous main line, hauling the same heavy trains that were the railroad's entire reason for existing. It performed the work. Engineers documented that it could do the job. But fuel and water consumption was unsustainable. Maintenance demands were beyond existing shop infrastructure, and diesel matched its output without any of its complexity. The John Henry was retired in 1957 and scrapped. The N&W placed its first diesel orders that same year. Like its namesake, it proved the point, gave everything it had, and then it was gone. Number 7. The Soviet AA-20 high-speed steam locomotive. The convention of high-speed locomotive design said that speed required mass, the largest possible boiler, the longest possible wheelbase, the maximum driving wheels the track would allow. Soviet engineers in the late 1930s approached the problem from the opposite direction. The AA-20, built at the Kolomna Locomotive Works in 1938, was a streamlined passenger locomotive designed for sustained running at 180 kilometers per hour, built not by scaling everything up, but by engineering every component, specifically around very high speed. One unit was constructed, designated AA-2021, carrying a 264 wheel arrangement and driving wheels 2,200 millimeters in diameter, approximately 86 inches, among the largest fitted to any Soviet steam locomotive. During trials on the Moscow to Leningrad main line in 1938, the AA-20 demonstrated high-speed running that exceeded the capability of any other Soviet motive power of the period. The results were considered promising enough to document extensively. Then, the Second World War redirected every engineering and manufacturing resource the Soviet Union possessed. The AA-20 did not survive the war period. No example is preserved. The fastest steam locomotive the Soviet Union ever built arrived at exactly the wrong moment in history, and the war erased it before the world had a chance to see what it could do. Number 6. The British Rail Advanced Passenger Train. Experimental. The rule of high-speed rail engineering said that faster trains needed straighter tracks. If you wanted to raise speeds, you rebuilt the infrastructure. Gentler curves, new alignment, upgraded formation. Speed was an infrastructure problem, and the answer was always more civil engineering. The APTE declared that speed was a physics problem. If a train could tilt its body inward on curves, like a motorcycle leaning into a bend, it could travel 40% faster on the same curve without throwing passengers from their seats. British Rail Engineering completed one 4-car experimental set in 1971, powered by 4 Leyland gas turbines, producing approximately 3,000 horsepower total. The entire structure was built from aluminum, and an active tilting mechanism operated on every passenger vehicle. On August 10, 1975, on a test run in Lincolnshire, the APTE reached 245.7 kilometers per hour, 152.3 miles per hour, setting a new British railway speed record. The tilting system functioned exactly as designed throughout the run. The experimental set was never replicated in that form. The tilting technology it proved was later developed by Fiat Ferroviaria and became the foundation for the Pendolino trains now operating across Europe and the United Kingdom. The APTE was built once, proved everything it claimed, and the physics it demonstrated now carries millions of passengers every year. Number 5. The Union Pacific Gas Turbine Electric, 3rd generation. The rule of American freight railroading by the late 1950s was diesel electric. Reliable, fuel flexible, maintainable anywhere with standard parts. Every major carrier was converging on the same answer. Union Pacific threw the diesel out entirely and replaced it with a gas turbine burning bunker C heavy fuel oil, so viscous and corrosive it had to be heated to 200 degrees Fahrenheit before it could even flow through a pipe. At room temperature, bunker C has the consistency of cold tar. General Electric delivered 8 third-generation units between 1958 and 1961, each consisting of 2 locomotive sections plus a dedicated fuel tender, producing a combined 8,500 horsepower per set. Nothing else on rails came close. Railroad workers called them big blows because the turbine exhaust was so loud a crew could hear one approaching from miles across open country. At their peak, Union Pacific estimated the turbine fleet hauled approximately 10% of the railroad's total freight traffic. Rising fuel costs and blade erosion from the corrosive heavy oil made them uneconomical. The fleet was retired between 1963 and 1970. One third-generation unit survives at the Illinois Railway Museum. Union Pacific built the loudest, most powerful freight locomotives in the world, ran them until the economics collapsed, and the last one sits in a museum in Illinois. Still enormous. Still strange. Number 4. The New York Central M497. The rule said locomotives were powered by established prime movers. Diesel engines, electric motors drawing from infrastructure. The engineering establishment had made its decisions, and jet propulsion belonged to aircraft. In the summer of 1966, the New York Central Railroad built a jet-powered train in 30 days by bolting 2 surplus jet engines from a Cold War strategic bomber onto the roof of a standard commuter railcar. The engines were General Electric J47 to 19 units, pulled from a Convair B-36 Peacemaker. The streamlined nose cone was designed by Ruth Wetzel, a commercial artist and wife of project engineer Don Wetzel, who had never designed a locomotive before. The 2 original diesel engines were kept running only to power the brakes and electrical systems. On July 23, 1966, with Wetzel as pilot and NYC President Alfred Perlman in the co-pilot seat, the M497 was officially clocked at 183.85 miles per hour on a 21-mile straight between Butler, Indiana, and Stryker, Ohio, an American rail speed record. As a safety measure, railroad ties had been placed across the track near Toledo to derail the vehicle if braking failed. Wetzel later stated the speedometer had peaked at 196 miles per hour before he reduced power. The jet engines were removed after the test. The car returned to commuter service and was eventually scrapped. 30 days to build. 1 afternoon to set a national record. And a railroad president in the co-pilot seat. Number 3. The French aerotrain IATHV. The rule of ground transportation. Every rule, from the first railways onward, said that vehicles required wheels. A mechanical interface between vehicle and surface. Everything that moved on land touched something solid with something solid. The aerotrain I-80HV had no wheels. It floated on a cushion of compressed air above a concrete guideway, propelled by aircraft-derived jet engines, and it traveled faster than any wheeled ground vehicle had ever moved. French engineer Jean Bertin designed the program around the belief that steel-on-steel contact was the fundamental speed limit of ground transport. Remove the contact, remove the limit. The I-80HV was the most advanced prototype, designed for 80 passengers, operating on an 18-kilometer test track near Orléans. On March 5, 1974, the IACHV reached 267 miles per hour, a world record for any air-cushioned vehicle on land. The French government awarded a commercial contract for a passenger line connecting 2 Paris suburbs. The contract was canceled less than 4 weeks after signing. France had chosen the electric TGV instead. Jean Bertin died on December 21, 1975, at the age of 58. The I-80HV made its final run in 1977. In 1992, the prototype was destroyed by arson. Sections of the original concrete guideway remain visible near Orléans. The machine that held the world land speed record for an air-cushioned vehicle was canceled, orphaned, and burned. The guideway is still there. The machine is not. Number 2. The Pennsylvania Railroad Q2 duplex freight locomotive. The rule said that the horsepower ceiling for reciprocating steam had been reached. Engineers had explored the limits of adhesion, boiler capacity, and mechanical stress. The records of the 1930s and early 1940s represented a permanent boundary. In the spring of 1945, Q2 number 6175 walked into the PRR's Altoona test plant and produced 7,987 indicated cylinder horsepower. That figure has never been equaled by any steam locomotive on a static test plant anywhere in the world. It remains, 80 years later, the highest horsepower output ever recorded for a steam locomotive under controlled test conditions. The PRR's Juniata shops built 26 units between 1944 and 1945. Wheel arrangement was 4664 duplex on a single rigid frame. 10 driving wheels powered by 4 cylinders, carrying a tractive effort of 115,800 pounds. According to railroad documentation, a Q2 could haul 125 freight cars at 50 miles per hour. That was 78% more powerful than any previous PRR freight locomotive. All 26 were out of service by 1951. Every one was scrapped by 1956. 2 number plates and 1 builder's plate are the only physical objects that document the existence of the most powerful rigid frame steam locomotive ever built. The record is permanent. The machine that set it is completely gone. Number 1. The Pennsylvania Railroad T1 Duplex Express Passenger Locomotive. Every railroad that needed more power from its express passenger fleet followed the same rule. Build a larger conventional locomotive. More driving wheels. Longer frame. Bigger boiler. Scale up what already works. The Pennsylvania Railroad looked at that rule and rejected it. The T1 divided its driving wheels into 2 completely independent powered groups on a single rigid frame, a duplex configuration pursued at this scale by no other major railroad, and dressed the result in a body styled by Raymond Loewy, the most celebrated industrial designer in America. The production models wore a shark nose profile so distinctive that photographs remain instantly recognizable 8 decades later. Not just fast. Not just powerful. A machine designed to announce that the Pennsylvania Railroad intended to define what a locomotive could be. Baldwin Locomotive Works collaborated on 2 prototypes delivered in 1942, followed by 50 production units in 1945 and 1946. Wheel arrangement was 4-4-4-4. During testing, a T1 generated 6,552 horsepower, 46% more than a conventional locomotive of equivalent driver weight. Prototypes routinely held 100 miles per hour with 13 or more passenger cars between Harrisburg and Chicago. The duplex drive split the driving wheels into 2 groups, each carrying less adhesion weight than a conventional locomotive, making the T1 violently prone to wheel slip at both low and high speeds. The poppet valve gear was nearly inaccessible for maintenance. By 1948, the PRR had committed to diesel. By 1952, every T1 was retired. All 52 were scrapped by 1956. Not a single example was preserved. A nonprofit organization, the T1 Trust, is currently constructing a brand new T1 from scratch, with completion targeted for approximately 2030. They are building a new one because no original survived. That is how singular this machine was, and how completely it disappeared. Every machine on this list was built once. Some set records that still stand. Some failed inside of 3 years. Some were scrapped so thoroughly that 2 number plates are all that remain. But everyone proved something about what the physics allowed, about what engineers were willing to attempt, about what it means to build a machine the world is not ready for. If you want to see more, click the video on screen now.